Let's talk about Kirchhoff's laws. We're going to start with a quick overview of what those laws are and the phenomenon they're describing, and then we'll take a look at some example questions. There are two specific laws we're going to look at. We're going to look at the current law, the KCL, or Kirchhoff's current law, and the KVL, Kirchhoff's voltage law. Let's start with the KCL. So KCL stands for Kirchhoff's current law, and it tells us that the total current or charge entering a junction or node is exactly equal to the charge leaving the node, as it has no other place to go except to leave, and as no charge is lost within the node. Basically, if we have current flowing into a wire, and we can make a little description drawing here. So we're going to have our wire, and we can also think of this as like a hose laying in your backyard. Whatever amount of water, that's our awesome water, enters the hose, it must also exit the other end of the hose. We're not going to lose any water along the way. Assuming we have no leaks, which is what we're assuming here, whatever water goes in must also come out. So water in, water out, and they must be equal because there's no losses along the way. And that's all that we're saying with Kirchhoff's laws. So we're going to have our mobile charge carriers, our little electrons, moving through the wire. And it's not really hollow, but for the sake of this quick description, that's fine. We have the electrons moving in the wire. We have electrons moving out of this zone. And our current in and our current out must be equal because there's nowhere else for it to go. The electrons can't just start jumping out of the wire and spewing out into space. So current in equals current out. And it specifically talked about nodes or junctures, or junctions. So let's take a look at what that means for a moment. Let's say we have some place in our circuit where our wire suddenly split, and we're just zooming in. So this is just like a part of a circuit. Obviously, circuits need to be closed loop, so this wire would continue somewhere, and this would continue, and this would continue, and this would continue. And it's somewhere along the way they'll meet back up, and we'll have some kind of battery or something. But just zooming in here to focus on this specific situation, just on the junction, we're going to say that whatever current is flowing in, so we'll just call this current 1, and then the current's going to split, so it's going to flow out through these three branches. So current 2, current 3, and current 4. I know that all the current coming in must be equal to all the current coming out. So I can say right away that I1 is equal to I2 plus I3 plus I4, because no charge or current is being gained or lost anywhere else in that junction. So they must be equal because the total amount of current or charge is preserved. Meanwhile, Kirchhoff's voltage law is telling us that in any closed loop network or circuit, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. So in other words, the algebraic sum of all the voltages within the loop must equal to 0. Let's see what this looks like by looking at a simple circuit. So in this circuit, I'm going to have a cell or a battery, a light bulb, and a resistor. So resistor is just basically many loads that we put on circuits or resistor, but you can also get devices that are called resistors, and they just adjust the voltage, or they just turn some of the electrical energy into heat or whatever. So what we're going to notice here is that we know that our battery is what supplies energy to the circuit. It induces a voltage. So in this case, we're going to say that our battery has a voltage of 2 volts. We're going to say that our bulb is going to use 1.5 volts. So it's using, so energy is going out of the system, so to speak. And our final resistor is going to be a half voltage drop across that. So if we add up all the voltages in the circuit, so we're going to have 2 plus negative 1.5 plus negative 0.5. That is going to equal 2 minus 2, or 0. So basically, when we go all the way around the circuit, the sum of the voltages must equal to 0. And just as an analogy to help us understand this, we can also think anytime there's a change in voltage, we're thinking about a change in the electric potential energy of the charges in the circuit. We can also think about that as height. So think if I have a charge that goes through a battery, its potential energy has been increased. So voltage is like a change in potential energy. A change in voltage is like a change in potential energy. We also have changes in gravitational potential when we lift something. So you can think about the battery being like a little elevator that lifts our little charges up and gives them more potential energy. That's not actually how it works. We're not actually lifting things. It's not a matter of gravitational potential. It's electric, but we can think of them as being kind of analogous. So going through the battery, getting a voltage bump is the same as or similar to lifting an object higher and increasing the height. So the way I like to think about this is if I go for a run and I start at home, I'm going to be graphing height versus time. I should put that on my 0. So height versus time. And this is going to be like elevation, like above sea level or whatever. So I'm going to go for my run. And I'm going to encounter a hill. And I'm going to gain a lot of potential energy. And I'm going to run at the top of the hill for a bit. And I'm going to run back down. And I'll go throughout my route, and there'll be some bumps and hills along the way. When I turn around and come back home, I'm going to go through all the same things again. So I'm going to encounter that bump that I encountered in the road. I'm going to encounter the big hill. And no matter what path I take, I will always end up at the same height I was at the beginning. So my gravitational potential energy started at some level here. It increased, then it decreased, then it increased, then it decreased, then it increased, then it decreased, then it increased, then it decreased. If I add up all those arrows, if I add up all those changes in gravitational potential energy, or similar to my circuit, if I add up all the changes in voltage, I'm going to end up right back where I started. So the net sum is going to be 0. And you might say, Mr. Strike, what if we don't go back around in the same route? What if I took a different route on the run? Well, let's see what that looks like as well. So, height, I'm going to start at some elevation above sea level. I'm going to go for my run. I'm going to go up the big hill. I'm going to come down the big hill. And then maybe I decide that I don't want to go up the big hill again, or I don't want to take the same route. I want to take a different way home. That's fine. Maybe there's some other hills along the way, some other bumps. Maybe there's a really nice downhill part, and then I'm walking at the bottom of a little hill for a while. No matter which route I take home, even if I end up going up a really, really steep hill, or I stopped and climbed a tree or something, whatever happens, I'm going to end back where I started in terms of my potential energy. So, something like that. And so once again, if I went through the whole route and I gained some potential energy, so it's like there was a battery, or sorry, yeah, that's right, I gained potential energy. So it went up, and then I went down, and then I went back up, and down some more, and then up, and then up, and then down. Once again, if I add up all those changes in potential energy and gravitational potential, it's the same as adding up all the voltages, and I end up right back where I started. So when I return home, I end up having the same gravitational potential energy. When the electron returns home from its trip through the circuit, it is going to have the same potential energy as when it started, which is what Kirchhoff's law is basically saying, that if we added up all the voltages, they will be equal to 0. The other important topic we need to discuss here is resistance. And so I'm just going to try to state plainly what we need to know about resistance. And that is, there's two situations we need to deal with. The first is if we have a bunch of resistors in series. So let's talk about series. Series is just when things are in order. So I'm going to have resistor 1, resistor 2, resistor 3, oops, resistor 4. Maybe we have a battery in between, and we want to know the resistance of this circuit. In order to find the total resistance of the circuit, we're just going to add up all the resistors that are in the circuit. So R1 plus R2 plus R3 plus R4. Things are a little different if we have it in parallel. So let's say I have my battery, and then I'm going to have it split, and I'm going to run like 3 different lights all at once. A light is just a specific type of resistor, and each of these will have a resistance, and then it's going to flow back to my battery. So we're going to say this has a resistance 1, and resistance 2, and resistance 3, and I'm just going to note that the total of the total resistance of this circuit here is going to be the sum of the inverse of each individual resistor. So it's going to look like this. It's going to equal 1 over R1 plus 1 over R2 plus 1 over R3. So anytime you're answering a question asking you to find the total resistance of the circuit or the equivalent resistance, you have to really pay close attention to whether it's in series. So if it's in series, we just sum up all the resistances. But if it is in parallel, we're going to need to work with the inverse, so the sum of the inverse of each individual resistor. So just make sure you memorize these formulas and make sure you're very carefully identifying which situation you're dealing with and choosing the correct formula when answering questions. Now that we've had a chance to look at the laws and the formulas involved, let's actually use this to solve a problem. So in this example, we're going to take a look at 2 similar but different circuits. One has resistors in series and one has resistors in parallel. I'm just going to talk through these diagrams first, just to make sure we can clearly understand what we're seeing here, and then we'll read the actual question and see what they want us to do. So it looks a little messy, but basically we're just going to focus on the path that the charges take around the circuit. Everything else is just labels. So focus on this part first. So we're going to have our cell or our battery. So our voltage is going to increase here. We're going to travel through the circuit. We're going to encounter some resistor. We're going to encounter another resistor. They're in a row, so they are in series. And then we just have a wire connecting the other end of the battery and completing our circuit. These labels here are just telling us that this is where we're measuring our voltage. So we're measuring our voltage across the battery on either end of the first resistor and on either end of the second resistor. And then we have extra information given here in terms of the amount of current going through each section of the wire, etc. Similarly, on our second example here, where our resistors are in parallel, we have our basic circuit. Once again, instead of having a single path, we have multiple paths, because that's what it means when we have things in parallel. So we can branch to the right here and go through this resistor, or branch to the left and go through this resistor. So they are in parallel, they are next to each other, there are multiple paths, and then we just have the wire going around and completing the circuit. And then once again, everything else here, it's just showing the voltage that's being measured here. So we have the voltage across the battery, the voltage across resistor 1, and the voltage across resistor 2. So if you actually have a voltmeter, you can just imagine we're placing the probes on either end. They're going to a voltmeter, and on its display, it's telling us what the voltage is across that resistor. Now let's take a look at the actual question. So previously we were given the total current and voltage information based on resistor data, which was withheld. Now we can see why the voltage of 3 cells, each 1.5 volts, equals a total of 4.5 volts if they are arranged in series. If we know the resistor values, R1 is 1.2 ohms, R2 is 0.6 ohms, we are asked to use both of Kirchhoff's laws and Ohm's law to find, so what are we trying to do here? We're trying to find the current and voltage at all parts of the circuit. So we're going to go through each of these circuits. We'll start with the series circuit, and then we'll take a look at the parallel circuit. So we're going to work with the series circuit first. And the first thing we're going to figure out is the total resistance. Now, we said before that it's really important to know whether we're dealing with our resistors in series or in parallel. We notice here that our resistors are straight in a row. There's a single path through them. It's also labeled that it's in series, so that's pretty helpful. And we can look back at our earlier note and see that when they're in series, we're just going to add everything up. So let's take a look. Our total resistance is going to be equal to resistance, there's only 2 resistors, so resistor 1 plus resistor 2. And we are given in the question the resistance of each of those resistors, so we can just plug that right in. Total resistance is 1.2 ohms plus 0.6 ohms. Therefore, the total resistance or equivalent resistance in this circuit is 1.8 ohms. And now that we know the total resistance and the total voltage, we can find the total current. So remember, V equals IR, and we have our total voltage and our total resistance for the circuit, so we can work backwards to find our total current. So we want to find the current, because remember it said find the current and the voltage for each. So total current is equal to V over RT. I'm just rearranging the equation here. We can plug our numbers in. We're told here that our total voltage in the circuit is 4.5 volts. So we can plug that in. Divided by that total resistance, 1.8, is going to give us an answer of 2.5 amps. And remember we said in Kirchhoff's law that whatever current is going into a section of the circuit, a node or a junction, must be what's coming out. And we don't have any split paths anywhere in here. So if I'm just going to investigate different parts of the circuit, if I was just to like make a slice through here and measure the circuit or current going through, 2.5 amps. If I take a look here, the current hasn't had anywhere else to go. It's still 2.5 amps. And here as I enter the resistor, 2.5 amps. And in the resistor, there's nowhere to go, 2.5 amps. Coming out of the resistor, 2.5 amps. Coming through the second one, everywhere we look, the current in this circuit will always be 2.5 amps. Now, since we know that the current or the amps everywhere in the circuit is the same, we can also look at each individual resistor and figure out what the voltage drop is across it. So let's take a look at our voltage. Let's do some voltage calculations together. So I'm going to have the voltage for the first resistor is just the current in the first resistor and the resistance of the first resistor. Now I know those values already, and I don't even need to rearrange the equation, so we can drop those values in. The current is going to be 2.5 amps because it's 2.5 amps everywhere in the circuit. The resistance, we were told, was 1.2 ohms for that first resistor. So 2.5 times 1.2 gives us a value of 3. So our voltage drop in the first resistor is 3 volts. And if we look at the second resistor, V2, I2, R2, once again, the current everywhere is 2.5 amps. The resistance in the second resistor is 0.6 ohms. And 2.5 times 6 gives us 1.5. So the voltage drop across the second resistor is 1.5 volts. And we'll also notice that we can kind of confirm or check our answer here because we said that the cells or the batteries were a total of 4.5 volts. And the voltage drop in the circuit is 3 plus 1.5, which is 4.5 volts. So once again, we can kind of think of it if we're walking through our path. The charges go through the battery, and so they get an increase in their voltage. They're going to travel through the circuit. They're going to go through the first resistor, and they're going to have a 2.5 or 3 voltage drop. So we went up. We're just chilling in the wire. We're going to have a voltage drop of 3.5, so we only have half a volt left of potential energy. We're going to go through the second resistor, drop even further down to 0, which is where we started. So that's fine. It's just like our walk. I went up at one part, I went down at another part, and I ended up right back where I started. So this is Kirchhoff's voltage law in action. All right, I've tidied up the screen a little bit now just so we have room to work with our parallel circuit. Once again, we're basically working with the same components. We still have, resistor 1 and resistor 2. They've just been rearranged into a parallel circuit instead of being in series. Let's take a look at what we're dealing with. Let's see if we can find the voltage and resistance and current at all the different points required throughout this circuit. We're going to start once again by finding the total resistance of the circuit. Remember, when we're dealing with parallel, it's going to be 1 over the total resistance is 1 over, well, the sum of the inverse of the resistances. We know we have 2 resistors, so 1 over R1 plus 1 over R2. Once again, these numbers are given in the question. I didn't take time to write out all my variables with their values, just because it's given really plainly in the question and I didn't have a lot of room on the page. Generally speaking, though, make sure you're identifying which formula you should be using, which values for the variables are given, which variable you're trying to find, and going from there. Now let's plug in our values. I'm going to have 1 over the resistance for resistor 1, which is 1.2, plus 1 over 0.6, once again, right here. Same numbers as before. We've just changed the physical arrangement of the circuit, so we need to use a different formula because it behaves in a different way. And if we add these all up, I'm not going to show all my work, but we know how to do the math. 1 over RT is equal to 3 over 1.2, which means if I find the inverse of each of these, I flip, we're going to see that total resistance is equal to 1.2 over 3, or 0.4 ohms. And we'll also just point out that the total parallel resistance is lower than either resistor. So each resistor is more than 0.4 ohms, but by arranging them in this specific way, we're able to achieve resistances lower than the value of any individual resistor. Now that we know the total resistance and we know the total voltage because it was given in the question, we can find the total current. So once again, V equals IR, and we're dealing with the total circuit. We were told in the question, actually let's rearrange first. It's usually good to rearrange before you evaluate. If that's something you're struggling with still, that is a really good skill to keep practicing, properly rearranging equations. It's going to be super important all throughout high school, especially in like any math or science course. Let's plug in our values. We know the voltage in the circuit is 4.5 volts. We know the resistance, which we just found here, is 0.4. So let's do the calculation, and we're going to find that it equals 11.25 amps. And we'll see in a moment how we can use that to do our next calculations. All right, let's take a look at each individual resistor. So we're going to have resistor 1 and resistor 2. I'm going to talk about what we know, and then we're going to get into the calculation. So I know the voltage drop across each of them. So if the voltage here was 4.5, the voltage from here to here, oops, sorry, wrong circuit. The voltage across the cell was 4.5. The voltage drop from here to here must be 4.5. So ultimately, what that's going to mean is that the voltage across each resistor is going to be 4.5. So voltage 1 is 4.5 volts. Voltage 2 is 4.5 volts. We know the resistance of each because it was given in the question, 1.2 ohms, 0.6 ohms, and now the piece of information that we're missing is the current. Because with Kirchhoff's law, I can say generally speaking that whatever current, goes through here and comes out here must be the same. Same thing here, whatever current enters the junction point and whatever current comes out here must be the same. So it's just like having our hose. Whatever amount of water goes in must also come out, but we have a branch here now. So maybe we have something like this, where we have a hose, and then we have a splitter. That is a terrible splitter. Let's try that again. So we have a Y splitter in our hose. I have 2 different branches of my hose, and then we bring them back together, and the hose continues. So whatever amount of water comes in at this end must equal the amount of water that's coming in this end. What we don't know is how much water is going through each of these. Maybe one of these pipes is really narrow, which we can think equivalent to being a much greater resistance. Maybe only a little bit of water goes through here, and a lot of water goes through this pipe. That's what we're trying to figure out right now as we do our calculation, as we try to figure out the amount of current. So we're going to use our good old trusty equation again, V equals IR. I'm trying to solve for I, so I'm going to rearrange. So start with the original equation, V equals IR. Rearrange and solve for I. I1 equals VI over R1, VI. V1 over R1. Let's plug our values in. Our voltage was 4.5 volts. Our resistance was 1.2 ohms, and 4.5 divided by 1.2 gives us 3.75 amps of current. Next resistor, we already showed our work rearranging the equation last time, so we can just go straight to our rearranged form. Let's plug in our values. 4.5 volts, 0.6 ohms of resistance is going to give us 7.5 amps of current. And what do we know about Kirchhoff's law? Whatever current flows into the junction must flow out of the junction. Let's just confirm that these add up to the total we're expecting. So total current is I1 plus I2 is 3.75 plus 7.5. And oh look, that gives us 11.25, which matches our answer from earlier. So that's a pretty good indication that we did this calculation correctly because our numbers are in agreement. And I believe that is about it for this topic. If you are working through this on Brightspace right now, there are additional check your understanding questions you can take a look at. There are answers provided there, and if you do have specific questions, please ask your teacher and they would be happy to help you.